So in this final video of this session about dictionaries from our algorithms and data structures course in Python, we will be speaking about dictionary efficiency, or as some students have put it over the years, do we really have to learn another data structure? Can we just use lists? Well, the short answer is no. And the slightly longer answer comes now. Basically, we could use lists to store mostly any kind of information, and lists are better suited for information that has this sequence characteristic, the shape of a sequence. But we could just impose sequence shape into any sort of data. We could just make up an order. But that would not be very efficient in order to retrieve our data. The structure that dictionaries bring to the table is highly valued because they allow us to access any part of their data, even if they don't have an order that we know of, very fast and very conveniently. Let's give an intuition. Let's suppose that we have a list as we used to, and we want to look for number 55. Okay, so what we did was traverse our list or do a search loop that goes looking at all the elements until one fulfills our condition or I run out of elements. So I would start at the first and see, is this 55? No. Okay, let's go to the second. In the second one, it would look again and say, is this 55? No. Okay, next one. And so on and so forth until I eventually hit the element that in my list is actually 55, okay? So in order to find an element inside the list, we need to look at all of them, potentially. So this has a cost. We will see a lot more about costs in the second part of this subject, but this has what is called a linear cost, a cost that is related to the number of elements, to the n, to the size of my data, okay? With dictionaries, what I want to have is this universe of keys, this universe of values, and the dictionary that puts them together. So I have lots of key value pairs in my dictionary. Many. Okay, each key is the door, is the way to access my value, the value that goes with it. So I will get one particular key and use it to very efficiently locate the key value pair that contains it, and that will give me access to the value that goes with this key very fast. Okay, what do I mean by very fast? Basically, dictionaries try to find keys without having to look at all the values, so I don't have linear cost like I had with lists. Ideally, a dictionary can find a key very fast only with a fixed number of operations, no matter how big the dictionary is. Okay, that would take some more explaining to see the details of, and if you're interested in this, which is really an interesting subject, I recommend that you have a look at the references about hash tables that you have in the Jupyter notebook. Okay, but this concept of being able to do something using a fixed number of steps is called constant complexity, or O of 1. Okay, so let's see how this works in practice. So we have the idea, okay, lists are bad because they are linear. Dictionaries allow me to potentially find keys in constant time. How does that work? Is that really so? Is there such a big difference? Let's use this code to answer that, okay? Basically, in this code, I will use some, let's say, artificial encoding of my information to have the same information inside of a list and inside of a dictionary. I will have a number of elements, okay, which I have determined to be 200,000. So this Jupyter notebook will run in a reasonable time, okay? And speaking about running, let's just start it running, okay? I am measuring the time, and what I'm doing first is generating data. Basically, for each of my elements, I'm generating a value using a uniform distribution from 0 to the number of elements. So in this case, it will be integers between 0 and 200,000. Okay, and then what we do is that we insert the value in a list. Okay, basically we insert a tuple of the number of element that I'm generating and of a random value. And in order for all of this not to be, let's say, just correlative, to be well sorted, I do some trick. Okay, if I have drawn a random value that's further than half of my number of elements, then I append it. I add to the list in the last position that I have. Okay, otherwise I insert it in at the start of the list. So basically I'm generating a list with random values and random positions, and I either insert at the start or at the end of my list. And as well as I do this, I just add to a dictionary. I add the key, which is the position, and the random value, which is the value. Okay, I have defined my large dict as an empty dictionary here, and my large list as an empty list here, and I'm appending to the list or inserting, and I'm adding key value pairs to the dictionary like we have just seen. Okay, and then I'm just going to search, as we have seen, in my list and in my dictionary. I'm going to have some time measuring functions, which you might look into if you want to, but basically they come from the time library. Okay, and they act as a timer. I start it and then I record it when I have finished what I am doing, and I see how much time has elapsed. In order to look for my tuples that contain the position and the random value in my list, I just use a search loop. Okay, classical search loop that we have seen quite a lot of times, with a boolean to finish when I have found what I'm looking for, and the length of my list to see if I have finished all my elements and the thing that I'm looking for is actually not there. I'm generating a random search key in every case, so it may or may not be there. Okay, and then I'm also looking for the key in my dictionary, and in order to do this I only need to access my larger dict with my key. Okay, and that will give me the value automatically. Okay, as I have already run this, data generation took me 324 seconds, and when I look for it in the list, it took me 0.007 seconds. Okay, when I looked for the key in the dictionary, it took me 4.22 times 10 to the minus 5. Okay, so 0.0005042. So much smaller. Let's see if we can do it with a slightly bigger value. Okay, let's try, for example, 400,000 elements and see how that goes. But this first execution has already given me some concrete proof of how different these things are. So this took a little bit longer to generate, and again this took 0.08 seconds to find in the list, 87 seconds, and I'm still 10 to the minus 5 to look for the same information, and we can check that the value found is the same for one particular key in my dictionary. So I have some concrete proof, some timing that tells me that finding for keys in dictionaries is much faster than looking for keys in dictionaries is much faster than looking for the same information in lists, because I don't need to traverse all of my elements. I can go more or less directly, and I get a time that doesn't grow with the size of data. Okay, I hope this convinces you about the goodness of using the advantages, not goodness, the advantages of using dictionaries to store my data. To sum up this particular session and the first part of the course, we have seen 3 different data structures: lists to implement sequences, tuples and name tuples to implement different aspects of the same idea, or to group and ungroup data in Python and use it with loops, for example. And today we have seen dictionaries that allow me to store any type of data as long as I give it some structure with some keys that I assign to my values, and look it up really fast and really conveniently. Okay, I encourage you to have a look at the exercises. Drop me an email if you have some questions. And in the second part of the subject, we will be speaking about complexity. What does it mean for an algorithm to be fast? What does it mean for an algorithm to be slow? How does the size of data that I have play into that? We will be seeing new algorithms, and we will be using our data structure altogether mixed list of dictionaries that contain lists and tuples. And we will be using them to do lots of things, including and very particularly sorting lists and sorting things. Okay, so this concludes the first part of our subject in algorithms and data structures, and see you in the first video of the second part.